Hey there, it's Shannon Matchick-Myers, and today we'll be checking out cylindrical and spherical coordinates. These coordinates are really great. I know they have trig in them, so don't freak out, but they're really great for triple integrals where you're finding, where they're a nightmare in rectangular coordinates, and they end up being much easier in these other coordinates. So that's kind of why you'll need them. So let's check it out. Let's warm it on up, and a couple of things you're going to want to remember. Just your basic right triangle trig. Remember that cosine of some angle theta is equal to the side adjacent over r, right? And that leads us to what? X is r cosine theta. And sine theta, similarly, is y over r, which gives us that y is equal to r sine theta. Groovy, groovy? Okay, so we'll be utilizing these, and so let's go ahead and we're going to convert this rectangular equation to polar form and sketch the graph by hand. Fun times. Okay, so what did we just say that y was equal to in polar coordinates? Beautiful. R sine theta. So we're going to square that because y is squared. And then another thing to remember is that r squared is x squared plus y squared on our unit circle. Or actually, it doesn't even need to be a unit circle for that. Cool, cool. All right, and then that's going to equal to 9 times x. So x we said was, awesome, r cosine theta. So this is where we got this info. Cool, cool. All right, so now, well, okay, let's start working it out. So r squared times sine squared theta is equal to 9r cosine theta. Now, we want to, why don't we go ahead and get everything on one side of the equation, and then we can also factor out an r. So we'll have r times r sine squared theta minus 9 cosine theta is all equal to 0. Cool so far? So you would either get that r is 0, or we would get, beautiful, that r sine squared theta minus 9 cosine theta is 0. And then isolating r, what would we get? We would get 9 cosine theta, right, when we add that to the other side. And then that would be multiplied to, and that would be divided by sine squared theta. And then rewriting it, we have r is equal to, well, we could write that as 9 times cotangent theta. That would take one factor of the sine function, and then times cosecant theta. Good, good? All right, awesome. So now with the graphing. So with the graphing, you're going to have r and theta, and it's kind of weird because you're typically plugging in theta first. So you're, these are, you could also write this as r at theta is equal to 9 cotangent theta times cosecant theta. Cool, cool? All right, so let's take a look at a graph and see if we can kind of get a feel for it. With this one, I mean, I don't know, we'll Well, we'll plug in some points that we know, and then we may end up needing to just we may end up needing to get some approximations anyway. Since sine theta is in the denominator here of our expression, we need to stay away from theta equal to 0, theta equal to pi, right? So, and theta equal to 2 pi, which is coterminal with 0. So why don't we start with, I don't know, let's start with maybe pi over 2 might be a good one. So at pi over 2, what happens to r? Beautiful, it's going to zero out. And so actually, we don't need to include this equation here because it's already included. Already included. So it's just redundant. All right, so we've got 0 pi over 2. So here, this is where your pi over 2 is. This is the pole where your angle of 0 radians is. Let's see which one is halfway through. I think this is pi over 3. Oops, sorry. Pi over 6. Pi over 3. And then right here we've got pi over 4. Cool, cool? And then if we have each of the rings can just be 1. So it would be like you'd have 1, 2, 3, 4, 5, 6, 7, and then 8 would be the last ring. So what we'll do is we're going, the distance r, the radius is 0, and that happens at pi over 2. So we just have a point at the pole. Okay. So now this is where it'll probably won't be as pretty. Let's see, if we have pi over 4, cotangent pi over 4 is just 1, and then cosecant pi over 4 would be root 2, correct? Root 2. So I'm just going to grab I'm grabbing a calculator. I'm just going to get some of these values and we'll graph them real quick. So for this one, I ended up getting 12.7 approximately. So that means each of these are going to have to be worth, what, 2, right? 4, 6, 8, 10, 12, 14. All right, so at a pi over 4 revolution, we'll be at 12.7, which will be about right here. I'll do it in a different color. About here. Cool so far? Alrighty. And then, so negative pi over 4 is going to end up being, what do you think? You'll end up with 2 negatives, right? So you'll still have your positive 12.7. Cool so far? So then we'll be down here. And then we're getting closer because we know we have a parabola, right? All right, so then if we go to pi over 3, it turns out being 6. That's nice. And then negative pi over 3, we're going to end up also getting 6. So let's graph those two, and then we should have a good enough picture for what we've got going on. So pi over 3 is this rotation up here, and then we got to go to 6. So we're right over here, and then over here. Cool, cool. So we've got our nice parabola, and it's going to, you know, increase quite rapidly. All right, cool, cool. So that's how, you know, a little reminder of how to graph by hand using polar coordinates. So now let's take a look at the new stuff. So the cylindrical coordinate system. In the cylindrical coordinate system, a point P in space is represented by an ordered triple. And that ordered triple is r, theta, z. R theta is a polar representation of the projection of P in the xy plane, and z is the directed distance from r theta to P. All right, so what you've got is you've got your let's say you have a point right here. So this is our point, this is okay. Okay, so let's say we have I don't know, this point here, or this is in the, you know, the plane. This is before we do our directed distance z. So this is our will be our r theta, okay? And so we basically have this going on in the plane. And so right here, this right here is our x, okay? And then r is this rotation right here. Or not r, sorry, that's theta, okay? And then y, that's what, about here. I'm not making these very well today, sorry. So this would be our y right here. And then now what you do is you want to bring this point up to get the P. You bring this up however, or where, you know, however high you want to go, you know, your point is for your z. So this point right here is xyz in rectangular coordinates, and it is r theta z in the polar coordinates. And then of course right here, this right here is your r. Cool, cool? All right, so that's just sort of a picture of what's going on. Conversion guidelines. If you're going from cylindrical to rectangular, like we said, x is r cosine theta, y is r sine theta, z is just z. Easy to remember. If you're going rectangular to cylindrical, you use r squared as x squared plus y squared, and then tangent theta is y over x, and z equals z. So let's do it. Let's do some problems. So our first one, let's convert the point -2, 2 pi over 3, 5 to rectangular coordinates. All right, so we are going to rectangular coordinates, right? So x is equal to r cosine theta, right? And remember that this is in the form of r theta z. So we have x would be -2 times cosine of 2 pi over 3. So x is going to be -2 cosine 2 pi over 3, I think is -1/2. And so x is equal to 1. Cool so far? All right, now let's do our y. Y is equal to r sine theta. And that gives us y as -2 times sine at 2 pi over 3. So y would be equal to -2 times √3 over 2. So y is equal to -√3. Cool, cool? All right, and then z, remember, is just so easy it's hard. Z is just z. So in this case, z is 5. Beautiful. So -2, 2 pi over 3, 5 is equivalent to 1 -√3, 5. All right. So next up, let's convert 3√3 -1 to cylindrical coordinates. So here we want to use r squared is equal to x squared plus y squared is going to be one of our tools, right? And this is x, y, and z. Now, what quadrant would these two be in? 3, √3. They're both positive, so do you see that would be in quadrant 1 for the plane part of it, the xy plane part of it? So we'll keep that in mind. And now let's figure out our r. So we'll have 3 squared plus √3 squared. So r squared is 12. And so r, being the radius, is positive, so you just, this will just be the positive, what do we have, 4 times 3, so 2√3. Cool, cool? All right. Now, tangent theta, this is where the quadrant will come into place, is equal to y over x. And so, tangent theta will be √3 over 3. And where in quadrant 1 does that occur? At what angle? Beautiful. Theta would end up being pi over 6. Cool, cool? And then z is just z, right? So z is -1. So we get that 3√3 -1 is equivalent to, in cylindrical coordinates, 2√3 pi over 6 -1. All right. All right, next up, let's find an equation in cylindrical coordinates for the equation x squared plus y squared is 8x, right? And that's given in rectangular. So let's see. X squared plus y squared equals 8x. Well, what is x squared plus y squared? Beautiful. Isn't x squared plus y squared r squared? And then x is awesome, r cosine theta. So here's that guy, and then this here is r squared. So then we would have r squared minus 8r cosine theta is equal to 0. Factoring out an r, you'd have r minus 8 cosine theta remaining. So r would be 0, or r minus 8 cosine theta would be 0. Isolating r, we would get r would equal to 8 cosine theta, but at an angle of, pi over 2 and plus n pi, where n is an integer, won't we get 0 for r on this one? So we don't have to worry about that one because it's, again, included in this result here, which is our answer. Cool, cool? Okay. All right, so let's go ahead and take a look at the spherical coordinate system. In a spherical coordinate system, a point P in space is represented by an ordered triple, rho, theta, phi. So rho is the distance between P and the origin, where rho is greater than or equal to 0. I should have numbered these. Theta is the same angle used in cylindrical coordinates for r greater than or equal to 0. And then phi is the angle between the positive z-axis and the line segment OP, where 0 is less than or equal to phi is less than or equal to pi. So note that the first and third coordinates, rho and theta, are non-negative. Or I'm sorry, not theta, rho and phi are non-negative. Rho is a lowercase Greek letter rho, and phi is the lowercase Greek letter phi. All right, conversion guidelines. So spherical to rectangular, x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. Rectangular to spherical, rho squared is x squared plus y squared plus z squared, tangent theta is y over x, and phi equals arc cosine of z over the square root of x squared plus y squared plus z squared. And then spherical to cylindrical, r greater than or equal to 0. R squared is rho squared sine squared phi, theta equals theta, nice. Z equals rho cosine phi. And cylindrical to spherical, r greater than or equal to 0. Rho is equal to the square root of r squared plus z squared, theta equals theta, and phi equals arc cosine of z over square root of r squared plus z squared. Okay, whew. So here we go. What does this all mean? So let's see what we've got going on. So we basically have sine phi is equal to r over rho, and then remember r is equal to rho sine phi, but r is also equal to the square root of x squared plus y squared. Cool so far? Now, y over r equal to sine theta, and so that remember gives us that r equals r sine theta. But what is r in these? Good. R is rho sine phi sine theta. Okay, z over rho equals cosine phi. So z is equal to rho cosine phi. And then x over r is equal to cosine theta. That's an oldie. So x is equal to r cosine theta. And then taking it into the spherical, we've got x is rho sine phi cosine theta. Cool, cool? Okay. So a lot of these ugly little things, you know, or not ugly little things, but a lot of these kind of mean looking things are just substituting in for r, right? So up here, when we had, you know, y is, whoops, r sine theta, and then this is r. And then we had over here again an r again. And it was, I think, rho sine phi, rho sine phi for each of these, rho sine phi. Okay, so let's take a look at what this looks like. Okay, that'll be easier to play around with. So here we go. Let's take a look at what we've got. We've got, of course, our x, y, and z, and then we've got in the you know, the plane, kind of like how we made it before, you'd have your x, you have some kind of, you know, x, y plane here. And so this here is x, x, and then y and y, right? And then we know that r goes in like that, right? So that's r. Actually, I don't need an arrow on it. So this right here is r. And then theta, I forgot what colors I used on the other one, sorry, is this angle here. So this is theta. Cool so far? Now we got to get to the z portion of it. That's r again, right? And then now you're going to have our rho come into play. And so rho is here, and the ordered triple xyz ends up being equal to our rho theta and phi. And phi is here. It's the angle that you make with the z-axis and rho. So that's phi. And then this here is rho. Cool, cool, cool? Okay. So here we go. Let's take a look at a couple more examples. Your main thing is you want to be able to switch back and forth, okay, between rectangular and these two coordinates. So let's convert the point given in cylindrical coordinates, 3, negative pi over 4, 0, to spherical coordinates. So, let's see what we got. So what we have here is we have r theta z, correct? So here, remember that rho is equal to the square root of r squared plus z squared. And we have both of those in there. So rho is equal to the square root of 3 squared plus 0 squared. So rho will just be equal to 3 because rho is given as positive. That wasn't so bad, right? And then remember that theta is just equal to theta, right? So here, so that was one of them. So theta equal to theta. So our theta is just going to be negative pi over 4. And then now we got to do a little more work. Phi is equal to our cosine of z over the square root of r squared plus z squared. So phi is equal to our cosine of 0, right? Because z is 0. And so what do we get for that? Beautiful. Phi is equal to pi over 2. Cool, cool? So now there you have it. 3 negative pi over 4, 0 in cylindrical coordinates is equivalent to 3 negative pi over 4 and pi over 2 in spherical coordinates. All right, so example 5, which is our last one. Find an equation in spherical coordinates for the equation x squared plus y squared minus 3z squared is equal to 0, given in rectangular coordinates. So let's check it out. X squared plus y squared minus 3z squared equal to 0. Well, what do we know about what these things are equal to? X is equal to, you can look back at your page if you need to, but remember that x was equal to rho sine phi cosine theta, but we're squaring it, so that would be squared. Y was equal to rho sine phi sine theta, and we're squaring that too, minus 3, and what was that z equal to again? You can look back if you need to. And then z is equal to rho cosine phi. And that's squared as well, and that's all equal to 0. So let's see what shakes out. We'll get rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. Oops, sorry. And then minus rho squared cosine squared phi equals 0. Now, what do you think? Can we factor anything out partially? I mean, I think we can certainly factor out from the first two terms. If we factor out a rho squared sine squared phi, aren't we left with cosine squared theta plus sine squared theta? Oh, and I forgot my 3. I'm sorry. Good thing I went to highlight. 3. Okay. All right, so then what we did here is that we factored, and then don't we know that cosine squared theta plus sine squared theta is equal to 1, right? So that'll be a good one. And then we still have minus 3 rho squared cosine squared phi, and that's equal to 0. So now we'll have rho squared sine squared theta times 1, right? Minus 3 rho squared cosine squared phi. Oh, excuse me, this is phi, not theta. Phi. And that's going to be equal to 0. Good so far? So if we factor out rho squared, we're left with sine squared phi minus 3 cosine squared phi equals 0. So we get rho squared is 0, or sine squared theta, or sine squared phi minus 3 cosine squared phi is 0. And so that would give us what? Sine squared phi would be 3 cosine squared phi. But then if you divided both sides to isolate that constant, do you see you'd get tangent squared phi is equal to 3. If you square root that, both sides, we would get tangent phi is equal to, so then what we'll get for phi, sorry I can't talk today, is going to be pi over 3. Cool? I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please subscribe.